Okay, so this is the second talk on day 4 of the hottest conference of 2020. And this talk, we have Anja Petković, who will be telling us, well, who's from the University of Ljubljana, and will be telling us about equality checking for finitary type theories.
Hello, everyone. Me to this wonderful event. I'm very happy that you organized it. It's been very nice. I've heard several good talks up to now, and I hope you all will learn something new and fun from my talk today. So I'll be speaking about equality checking for finitary type theories, and this is joint work with André Bauer and Philip Hasselwater. They are both here. Philip is waving, and I'm sure they'll be happy to answer some of the questions in chat, but I also encourage you to just interrupt me if something is unclear or if you have a question. I'd be happy to get some feedback. All right, so to start, I'll say equality checking algorithms are essential parts of proof assistance because they free the users from the burden of proving judgmental equalities, and they provide this sort of computation by normalization engines. And when I say equality, I will mostly refer to judgmental equality. So unless other specified, I keep in mind judgmental equality. And indeed, most popular proof assistants provide these equality checking algorithms for their underlying type theory. So here I listed just a few, like Coq, Agda, Lean. There are, of course, several others. And some systems go even further, and they allow user extensions to the built-in equality checkers. These extensions can be maybe unsafe, but they allow you to experiment with the equality checking algorithm a little bit. And such examples are Agda and its rewrite, and of course Didacti is sort of rewriting heaven. And this is all very nice, but what happens with user-definable type theory, like the one we have in Andromeda 2? So here we don't provide an equality checker for a fixed specific type theory, but sort of a general class of type theories, right? And we came to this problem, and what we did was we designed a user-extensible equality checking algorithm, and it's based on the type-directed equality checking that several people have done. We'll follow the approach of Harper and Stone, but I will not go into history of what happened before. And what we did was make these existing algorithms configurable by the user to have something in Andromeda, right? Because we can define our own rules. And for the usual kinds of type theories that we can present in Andromeda, like simply type lambda calculus or Martin-Löf type theory, the algorithm behaves like the well-known standard equality checkers, right? So no surprises there. But we designed it and we also implemented it in Andromeda 2 in the way that the user only needs to provide the equality rules they want to use, and then the system automatically classifies them in a suitable way. We'll see at a later point what I mean by that. And then it devises the appropriate notion of the normal form that goes with it. So it really is supposed to be user-friendly, what we have done in Andromeda. So this is the overview of what I'll be talking today. First, I will tell you what I mean by finitary type theories in the way that they are at the end implemented in Andromeda. So in this part, I will basically specify the setting that we made this algorithm for. And it's a little different from what Peter was talking in on Monday, but I will explain how. And in the other part of the talk, I'll give you the overview of the algorithm, its type-directed phase, its normalization phase, And I will tell you a little bit about the normal forms we get at the end. And a third part, the last part of the talk, will be a live demo. So I will be using this implementation of equality checker in Andromeda 2, and I'll be just using it. I will not show you what's under the hood, but I'll show you how you can use it later on. Okay, any questions so far before I dig in? Not yet. Okay, so let's start. What I mean by finitary type theories is an adaptation of general type theories that Peter Lambsdane was talking about on Monday. And with a little caveat, we take only finitary rules and finitely many of them. And this is because we want to implement this in Andromeda, and this is the setting we have. So because I know you all very well remember all the details about Peter's talk, I will of course summarize what I need from him, but this is sort of the general setting, right? What are the general type theories that Peter was talking about, but their finitary version. Okay, so he told us something about 4 hypothetical judgment forms. So we have these, A is a type, a little a is of type big A, equality of types, A, B, and equality of terms. And then he also explained that we have boundaries for these hypothetical judgment forms. And this is basically, they give us sort of the data that is needed to say, okay, this judgment is well formed, right? So when I say A is a type, I need nothing much, but when I say little a is of type big A, then I need to say, okay, big A is well formed, and so on. And here I have boundaries for equality judgments. And I have these little question marks up here, but really we're doing proof irrelevance. So I could delete these questions and just say, okay, these are necessary. It's not like we're inserting a proof here, right? What Peter didn't say, and is maybe useful to think of as a programmer, when we're using the implementation, we can think of boundaries as sort of an unfinished goal, right? So we need to provide a type, right? We need to provide a term of this type. We need to certify or derive this equality or the term equality. And with these judgment forms and boundaries, we also have well-presented inference rules. Again, I'll say they're finitary and finitely many of them. And by well-presented, I mean what Peter was talking about. For those who didn't listen to Peter's talk, I'll just say they're the usual kind of rules that we see given with fractions, and basically they make sense, right? So the next premise can be sort of type checked in our head with the previous premises and so on. So it's really nothing scary. Okay, so this is the general setting. But in Andromeda 2, it's an LCF style proof assistant, which means we sort of have a meta language with a type of judgments, and then we make those judgments by applying constructors to its arguments and so on. And specifically in this style, we don't carry a proof state, right? And if we don't carry a proof state, there's really no global contexts in the traditional sense. So this is not something we stumbled on the first time. So there is a context-free presentation that is suitable for this framework. And so previously it's been done for calculus of constructions, and it is the gamma infinity calculus that was done by Herman and the rest. But we sort of generalized this, not just for calculus of constructions, but in the Andromeda, it's implemented for these finitary type theories, right? And what we do in this context-free presentation is that there are no explicit contexts, but rather free variables are tagged with their types. So when I have a free variable A, I tag it with its type, say big A. Okay. So I will give a bit more detail about this context-free presentation because it has a couple of subtleties that are different from the usual setting. But really, for all the details, please take a look at Philip Hasselwater's dissertation, this guy here, and this person that is also has waved in the beginning of the talk. So Philip is here if you want to ask him questions. I'm sure he'll be happy to answer the details in chat or after the talk or even during the talk. But I will provide the necessary detail I need for the rest of the talk. But it's really, you know, it's nice work what he did with the context-free presentation. So it's worth taking a look. Okay. So what I mean by context-free, right? It's not just that I get rid of all the context, but if you take a traditional look, a look at the traditional rule for pi, I have these gammas here that I colored in red and we'll get rid of them. But we also have this sort of local context, right? That x is of type A and sort of that B has a bound variable x in it somehow. And we don't want to get rid of that because we still want to state these rules. So we only get rid of the gammas, but we have an abstraction as a primitive notion, right? So these local contexts we keep and we abstract judgments explicitly. And so we still have bound variables, but they all need to be properly abstracted away. So we use these curly braces as a notation for it. And here, when we have arguments of pi, we have to fully annotate everything. And the argument here is abstracted. And the rule for pi tells us it needs to be of type of the first argument, right? So I don't write x colon A here because I know this x has type A, which is the first argument. So this is how we're going to write it. So this is like the primitive notion of an abstraction. So we don't write these gammas. Even traditionally, we sometimes leave them out because they're really not necessary. But in our setting, really the free variables are taken care of by annotating them. And the local part of the context is taken care of by the explicit abstraction. Okay, so in the context-free presentation, I have these, again, 4 judgment forms with boundaries, and I have this weird bi-alphas here that I will comment on a tiny bit later. But we also can abstract judgments and boundaries, so we can stick in abstractions before that. Okay, so what is the deal with these alphas, right? And here, when we have boundaries, we also have by box, right? There's another hole in there. And I'm saying we're still doing proof irrelevance. So what do we stick in here? Well, all we did was got rid of the context. So let's take a look of the contexts again. So they have 2 roles, contexts. One is keeping track of types of variables. And we took care of that by tagging the free variables with their types and by explicitly abstracting bound variables. So everything is fine. But there's another role, and this is keeping track of which variables are available, right? Which variables we used when we derived some judgment. And annotations solve this first thing, but this second point we need to take care of. For example, in this general setting, the user can decide to pose equality reflection rule, right? That we see here. And this is written in sort of the traditional form with context and everything. But so the equality reflection rule says, okay, I have a type, I have 2 terms of this type, and then I have an element of its identity type of the equality type, and then it reflects back to judgmental equality. And here in the conclusion, P is not recorded, right? So if there were any variables mentioned in the derivation of P, we don't get to see it in the conclusion. So instead, we have to sort of keep track of that. And for tracking these variables that were used, we use assumption sets. So these are the alphas I was talking about before. So equalities, we say A equals B by alpha, and this alpha is an assumption set that consists of the free variables, the bound variables, and the meta variables. And we read it in the way that if we combine all the free, bound, and meta variables that appear in A, B, and alpha, and we make a union of them, then we get all the data that was needed to derive this particular judgment, right? So this is, in the assumption sets, we don't necessarily have all the free variables, but those that are not mentioned in A and B, and were still needed to be there in the derivation. Okay, so now we have tagging the variables, we have abstractions, and we have assumption sets, and we need one more thing, and these are explicit conversions in terms. Okay, so we got rid of the context, and this means that because we have assumption sets in equalities, when we convert a term, we have this syntactic feature, and we need to be explicit about these alphas in conversions as well. So here we have the rule, we have two types, we have T of type A, we have that A is equal to B by some assumption set alpha, and then I have, okay, we have this term, this is a conversion of T to B by alpha, and it's of type B now, right? So we need all these things, and we get some interesting aspects of these conversions. Namely, we get to make certain choices that it's not entirely clear what we should choose, right? For example, here I have a congruence rule for pi, and this is sort of the traditional form. I will say here loud and clear that this rule for pi, the congruence rule, is not complete because we have further premises, right? We have a premise that A is a type, that A prime is a type, and we say that A equals A prime, and then I have to say that B is a dependent type over A and B prime is a dependent type over A. I left those out because it gets too much, but I'm just saying they're there. But essentially when we state a congruence rule, say, okay, if the first two arguments are equal and the second two arguments are equal, then if we apply the constructor over them, we get this, right? This traditionally goes all well with the context, but if we have explicit conversions in the context-free presentation, we sort of can make a choice between two places or more to put the conversions in, right? So this rule is already sort of left-leaning congruence rule, right? Because I have X in A here, right? I don't have X in A prime. But furthermore, when we have explicit conversions, I can put the conversion in the conclusion here or in the premise. So let's read this in the context-free style. So A equals A prime by some assumption set alpha. And then abstracting over X in A, I have B of X is equal to B prime of X by beta. And now this B prime expects an X from A. However, here in the conclusion, I want to say pi of A prime B prime, right? And this X here, when it's abstracted, expects a type A prime, right? Because this is what pi rule gives us. So if you want to use B prime, you have to sort of explicitly convert this X here and say, okay, this is X of type A by alpha, because we have to feed something in A to B prime. And A and A prime are judgmentally equal, which is all perfectly fine. But we have to be here explicit. We have another choice in giving the conversion in the premise, right, here. So I could also say, okay, the conclusion needs to be pi of AB equals pi of A prime B prime, but we'll take care of the conversions in the premise, namely, okay, I know that B prime needs to expect something from A prime, right, this X is type A prime, but when we give the equality, we say, we need to abstract this equality over the same type, right? So we give an explicit conversion in B prime. So there's some interesting underlying features
think
that.
Bob Harper raised his hand, so
Yeah,
sorry,
sure.
I should. Bob, if you have a question,
Yeah,
feel free to unmute.
sorry, just a tiny question. The material in red is meant to be a substitution for X. Is that the idea?
Yes, yes, that's a substitution for X.
Okay,
Yeah.
okay.
I will write these. Yeah, I'm a bit sloppy in the notation, but yes, when I write here b prime of X, I mean, yes, this is substitution for X. Okay, if there is anything unclear in the future slides regarding the substitution, please ask me, because I'm sure I will do the same thing in future today. Okay. Right, so we have finitary type theories with context representation, which gives us these four things. So free variables are annotated with their types. Bound variables are abstracted with an explicit abstraction. We have the assumption sets that record which variables were used in the derivation in a way. And we have explicit conversion in terms. And this is the setting that we'll be working on. So before I go on to telling you all about the equality checking algorithm, that was the time for any questions regarding the finitary type theories that I've presented so far. Take a sip of water and then. Okay, so now we can actually take a look at what's with the equality checking algorithm. Okay, so here is the overview of this algorithm. So it has several mutually recursive sub-algorithms. So some are regarding normalization and the others are regarding equality checking. Okay, so we can normalize a type, we can normalize a term of a certain type, and then we can check equality of types or of their normalized versions, right? We can check equality of terms and of their normalized versions. And in the equality checking of terms, we have these two phases, a type-directed phase and a normalization phase. And these sort of all call each other. So I will explain a little bit more about what each of these does. So this first is the normalization part, and it works similarly for types and terms. We use computation rules as long as any apply. And I will explain in detail what I mean by computation rules, but these are basically beta rules, rewrite rules, whatever you want to call them. I will be precise about how they look. And then if there are no more computation rules, then we normalize the normalizing arguments, right? So the normalizing arguments are sort of the arguments that we choose needs to be normalized, right? So the user has to specify which arguments need to be normalized. And I will say a few more words about this when I discuss normal forms, but you can just imagine the user saying, okay, for this constructor, arguments 1, 2, and 3 need to be normalized, and the rest not necessarily. Okay, and this normalization outputs a certified equation between the original and the normalized expression, right? So we're not just outputting the normalized expression, we're actually outputting the equation between them, right? This is especially important because in Andromeda, the kernel checks this equation, right? So, okay. And then we have the equality checking. So here I had the normalization and the equality checking. So when we check equality of types, we first normalize them and then compare. And once we normalize them, we compare them structurally, which means that we apply a suitable congruence rule. And the arguments are compared recursively in the sense that the normalizing ones apply the algorithm, and the non-normalizing ones just take the congruence rule and so on. So we first normalize them and then we try to use the congruence rule and proceed recursively on the normalizing arguments. Okay, sorry. And then when we check equality of the terms, it gets a little bit more interesting because the terms, both terms appear at the same type. So we have first the type-directed phase when we normalize the type and then apply extensionality rules. So I will explain in detail what we mean by extensionality rules. But the pattern matching first appears on the type, and once we're done with that, we enter into normalization phase when we normalize both terms and then compare the normal forms, right? And then when we check equality of the normal terms, we just compare them structurally similarly to the types, right? So here, after the normalization phase, we check equality and it just goes structurally and recursively on the arguments. Okay, so I have several things to explain now, right? This is sort of the overview. I have to explain what I mean by this computation rules. I need to specify what I mean by normal form. I have to tell you what I mean by pattern matching on extensionality rules. And then you pretty much have the idea of what we do. Okay, so I'll start by this extensionality rules here, right, in the type-directed phase. And extensionality rules, broadly speaking, say that two types or terms are equal when their eliminators are equal, right? This is like the idea. And when we try to tell them when we try to explain them formally, we say, okay, they have this form where these are object premises and these Q's here are equality premises. So I'm not sure if I explained exactly. Peter already mentioned it, but I'll say it again. Object premises are the ones that introduce types and terms, and equality premises are equalities between types and equalities between terms. So this is their general form, and furthermore, we require that every meta variable that appears here in the object premises also appears in A here, because we will pattern match against this A and we'll say, aha, we need to know how to use this extensionality rule, right? So we pattern match against A and then recursively check these suitably instantiated versions of these equalities Q1 to Qm. Right? So here, again, I'll point it out. When you have a type-directed phase, we normalize the type, then we pattern match it against extensionality rules. We pattern match against this type, and then we can say, oh, we can apply this rule, so we proceed sort of recursively on these equality premises and we instantiate them appropriately as the pattern matching tells us to do. Okay, so extensionality rule for dependent functions would look like this, just as an example, so you really see what I'm talking about. So this is, we have a type A, a dependent type over A that is B. Then we have two functions, dependent functions F and G of type pi AB. And when we apply them over some X that is abstracted here, we get the same thing, right? So sort of if for every X we apply them and we get the same thing, then the functions are equal. So this is extensionality rule for functions, and here I have a footnote saying it's not to be confused with function extensionality because that one mentions identity types, and here I only mention judgmental equalities. Okay, so it's the extensionality rule, not the term. Okay. So the next thing I want to say is, right, this side note, these extensionality rules are interderivable with eta rules. So we don't use eta rules as some people might be thinking, oh, but they're essentially the same. It's easier for this algorithm to have extensionality rules because we have this type-directed phase that these provide. And we can derive eta rules from extensionality rules and vice versa in the presence of computation rules and congruence, right? So we need both of these to say, okay, we don't need eta rules, extensionality will be enough, right? So I will show this later in the implementation in Andromeda for pi types, right? We will give the rules for pi types. Here we have the extensionality rule, we'll give the computation rule, and then we'll just let the equality checker derive the eta rule for it. Okay. So the computation rules are the next. So they have the following forms. This one is for terms and this one is for types. So we have, in both cases, object premises only, so no equality premises. And the left-hand side needs to be of the certain form. So in the term case, U has the form S applied to some arguments where this S is a term symbol. And in the type case, the left-hand side A has the form big S that is a type symbol applied to some arguments. And again, furthermore, all the meta variables introduced by the premises need to appear in these arguments inside. So when we pattern match against the left-hand side, we want to know, okay, this is what we have, this is what we will compute to, and we need to know that we can apply this rule. So it means that in these arguments, we need all these meta variables appearing so we know how to apply the rule, and the pattern matching is sort of clear. And here is an example. So what is a computation rule for dependent functions? Well, it's just the usual rule. So if we have lambda and an app, then it's the same as just the substitution. So we have a type A, a type B, and then we have here S that is subtracted over A and is of type B of X. Then we have a term of type A, and then we do this, right? We have app AB. This is all fully annotated, and so we have app of lambda is the same thing, is S, right? When we apply to A and have S when A is substituted for X. Nothing new here. I'm just reading it out loud so people can take a breath and internalize what computation rules are, right? So I will slowly say it again. Here in these premises, all the meta variables have to appear in the arguments as well, right? This is very important. Okay. So once we have computation rules, right, we need to say what normal forms look like, right? Because here in the algorithm, I said, okay, use computation rules and then normalize the normalizing arguments. And what you get at the end, what are the normal forms? Well, it's basically this, right? So an expression is in normal form if no computation rules apply anymore and its normalizing arguments are in normal form. So this is our definition. So in fact, this definition depends on what we selected as normalizing arguments. So they specify what is sort of weak normal form. But if we say all of the arguments are normalizing, we just get the strong normal form, right? So there is a question of how to pick which arguments are normalizing, right? So we can just pick everything, we get a strong normal form, or maybe we can do something less. And in Andromeda too, we actually have like a default way of choosing normalizing arguments, which is basically if we have a symbol applied to some arguments, normalizing ones are those that are not immediately meta variables. So here I'll give an example. So this is the same computation rule. And for app, we have here 4 arguments and we say, okay, Andromeda will say, okay, this is just a meta variable. This is just a meta variable. This is not just a meta variable. This will be the normalizing argument, right? And this is again just the meta variable. So just the 3rd argument will be selected as the normalizing one by default in Andromeda. But basically the user could say something else, right? So it really depends on the user which arguments we pick to be normalizing ones, and then the normal form at the end will depend on the choice.
So this the default choice depends on the computation rule and not just the symbol.
Yes.
Right. Okay.
Yes.
But the definition of normal form applies to an expression. So like, do you take the information from the computation rule and use that to attach something to the symbol?
So once we, so the normal form will be defined once we've installed all the computation rules and all the, yeah, basically all the computation rules, right? So once we've installed all the rules we want to have, then we'll say, okay, our equality checker thinks the normal form is the following, right? So when no computations rule apply and no more, so and all normalizing arguments are in normal form. And once we install the computation rule, we have to say, yes, the normalizing arguments are this, this, and that. This is the idea. So the normalizing arguments are decided at the time we install the computation rule. I hope that answers your question, Mike. Yes, that's perfect. Okay, thank you for the question. This was very good. Okay, so now we know all the necessary ingredients, but there is some things that happen under the hood, and I will just show one technicality of this equality checking algorithm that appears as a consequence of the context-free presentation. And this is, how are we normalizing abstracted arguments, right? Something interesting happens here. So I will explain it on an example. And this will be, of course, our running example for pi. So we have, we want to normalize pi AB, right? And how do we do that, right? So if we take a look at the algorithm, it says, okay, we normalize its normalizing arguments because we have no computation rules for pi. So we normalize A and we get some equality. A equals A prime by alpha, and this A prime we know is in normal form that equality checker believes is the normal form, right? Okay, and then we normalize the second argument, right? And this one gets a little more tricky. So we abstract over the equality and we have b of x equals to b prime of x by some assumption set beta. And now we want to say, aha, now we want to say, well, let's make pi of a prime b prime, right? And then I'll say pi of, here instead of a, I'll put an a prime. Then when we have x abstracted, it will expect to be of the type a prime, but our b prime, here the x has type a, right? So it's a similar kind of thing we encountered in the congruence rules, right? So what we need to do is first to convert this x in b prime, right? And we get pi of a prime and then b prime where x is converted to a by this equality alpha that we got, that a is equal to a prime, so that b prime, you know, gets something of the right type. Okay, and then we apply the congruence rule and we combine this into the judgment that pi ab equals pi a prime b prime, and then by beta where we take out the x. Okay, so it really, the conversion rules appear in the normalization process as well, because we need to be careful what boundaries the arguments have, right? Because something that Peter also mentioned, we sort of make the terms or types, right, expressions by applying constructor rules, and then the boundaries of the next expression sort of depends on the previous expression, right? So we have to be careful when we are normalizing that here we have a prime and not a, so we have to convert it into the appropriate type. So this is one place where it happens. Also, if we had an argument that is a term expression, we also need to pay attention to the type of this term, right? So it is another thing that happens. Okay.
May I ask what is meant by the backslash? I'm sorry, beta backslash?
Oh, this is just the minus in the sets, right? So it's difference. What I'm not sure what's the English word. So this is a set of assumptions beta without x, right? Because this beta is the set of assumptions, which is like free variables, bound variables, meta variables, and we take x out of it because it's
in
not
English
necessary.
it's called the set difference.
Set difference. Thank you. Thank you. Okay. Thank you for the question, though. Yes. Okay. So this is what the algorithm does. And I'll say a few more things about what we have not done. And this is that the confluence and the termination of normalization are not checked, right? So the user may import and install any rules they want. We don't check for confluence, we don't check for termination, and it may just loop forever, right? So we may try to add some support for checking of confluence and termination for the normalization, right? Also, when we have the type-directed phase, right? Here, I will show you exactly. Sorry. Here in the type-directed phase, we apply extensionality rules, and these equalities should sort of decrease in some well-founded notion of size for this to be complete, right? So these concerns are not in the system. These are external. I'm talking about specifically Andromeda here. We don't check that yet, but it's an interesting direction to go. We have also not yet really tested the efficiency of the algorithm. So since Andromeda is more of an experimental proof assistant and it's meant to sort of experiment with type theories, we cannot really compete with the efficiency of Cox equality checking algorithm or something like that. But maybe we can find some opportunities for optimization. We should also definitely check that. And currently the pattern matching is sort of not optimal, so we could make the algorithm extended to cover more complex patterns than we currently do. So these are sort of the directions we may go in the more or less near future. Okay. So, right. Now I would like to start with the final part of the talk, which will be the demo. So if anyone has some questions about the algorithm itself, now is the time. I will again have a sip of water and listen to you.
I was tinkering with type equality like this in dependent types in the 1980s. What I did about termination of normalization was just set up a counter, and after it counted for a while of normalization steps, it gave up and said, this is too complicated. That was straightforward.
Yeah, you could modify the algorithm in such a way to account for that easily enough.
Okay.
May I ask what happens with positive types?
I'm not sure what you mean by that.
Sums, for example. Oh.
Soundness of positive types.
Yeah, A plus B or whatever.
No, co-products.
Co-products, whatever. Okay, right. For this conference, I should have said co-product.
So if I have a co-product, if I have A plus B, like a dependent sum or something, I can just install the rules and go ahead.
I didn't mean to. No, I didn't mean to. Yeah, there's this unfortunate terminological snafu about dependent sum and dependent product. Oh my God, that'll never be resolved. No, I just meant like Booleans. I don't know. How about Booleans? 1 + 1 being 2.
Are you asking about there not being an extensionality rule for them?
Yeah, exactly. What did the algorithm do? I mean, I've been there and suffered this, so that's why I'm asking.
Well, if there is no extensionality rule, then there is no extensionality rule, and the type-directed phase will not apply.
Well, in actual fact, there is one, and in the case of Booleans, it's called the Shannon expansion, and it's what they do in model checking, like up the wazoo. And but the problem is what you do in the case of like any finitary sum, I'll use sum, sorry, coproduct, whatever you want to say. The analog of the Shannon expansion is quite the monstrosity because it involves basically pivoting on all of the variables of some type in a nested manner. It's like becomes a horrible thing. And then when you do inductive types, that's a further example of a similar phenomenon, and then it becomes impossible. It becomes infinitary. Sort of sums are sort of finitary inductive types. If you have an infinitary inductive type, then the whole idea like breaks down in a sense. However, in your setting with the way you're treating
yeah,
equality,
I don't think it applies. I don't think it applies to our setting.
Oh, okay.
Sorry?
Well, okay. So I must be missing something. So, all right. Maybe I should just stop.
Yeah, I recommend you go on since Anja, since time's running a bit short, and we want to see your demonstrations.
Yeah, well, basically what I meant to say is that I don't think the algorithm would handle that case, right? Because if you cannot input the extensionality rule in the way that we presented it, then it won't fly. Okay, right, so I will just say a little bit about the implementation. So it's implemented in OCaml in about 1,300 lines, and the equality checking algorithm itself lies outside of the trusted nucleus, right? So the nucleus checks every step, and it certifies the equalities that go on, so we don't really break anything. The worst thing that can happen to you is the equality checker just, crashes and says, I don't know what to do, or that it cycles because, well, we don't really guarantee termination. Okay, so I will, what I wanted to show you is a little bit of the equality checking algorithm for pi types. And since we're running a bit short on time, I will not type in everything, but I will just start, and then I will show you the code from somewhere else. So what we do is to install the equality checker in Andromeda, we say require ec. This is the equality checking module, and these double semicolons are part of the syntax. The syntax is very similar to OCaml's. And just a moment. And then I say, I'll just say what the rules are, right? Because we have nothing in Andromeda that's, we only have basically the structural rules and not anything else. So I have to say what pi is, right? So I have to say rule pi, and it takes a type, and it takes a dependent type. So I say x in B, x in A, B is type. Sorry. Okay, and what we get at the end is type. Okay, this is how I pose the rule for pi. And I'm pretty sure you can imagine how I would write the rest. So I'll just cheat a little bit and copy the rest of the code I wanted to show you. And I will read through it so you will see what I mean. Okay, so we have the rule for pi, and here is the rule for lambda that you have seen about 3 times in my talk already. So we take a type, an abstraction, B is a type, and then we have over an abstraction x is in A, we have E in B of x, and then what we get at the end is something of type pi AB, because pi we have already said what it is, and I need these as well. Then we have app, we take A, we take B, we take something in pi AB, we take something in A, and what we get at the end, at the application, is of type B of A, right? So this is the instantiation. And then we say, okay, this is the beta rule or the computation rule. We say pi B, this is how I call it. I take A, B, S, A, and this is the computation rule I gave earlier, right? So it's exactly what you would expect. And what I do next is say, okay, ec.add rule pi beta, and it just installs this computation rule. So I'll put a comment here. So I can actually run this code before. I'll say test.m31. Test already exists. Okay. Replace. Okay. And now I can run Andromeda, and I say, okay, run Andromeda native and go to Anja test.m31. And here is what happens. Okay, first it installs a bunch of stuff from the equality checker. And here is where the magic actually happens, right? So it says rule pi is postulated, lambda is postulated, app is postulated, beta is postulated. And we say, okay, term computation rule for app, and it says heads at 2. This means normalizing arguments. It's an old terminology. And it's the third argument because we start counting from 0. And then it gives you, okay, this is the computation rule. It's basically the same as this pi beta here. It just says derive because it installs it as a derived rule. We can install derived rule as computation rules as well. Okay, and then we put in the extensionality rule. So this is what we have, A and B. We have two functions, A and G of type pi AB. And we have that if we apply them on X, we get the same thing. Then the functions are equal. And then I can say, okay, now equality checker, please add this extensionality rule. And when I run this, it will says, very nice, rule pi X is postulated, and extensionality rule for pi is basically, it's installed. Okay. So now what I want to do is derive, so this will be the highlight of the implementation, right? I promised you that I will show you that we can derive eta from extensionality and computation rules, right? And we also have congruence rules in the back. So I say this, so I say, okay, let eta be, okay, and I will give it as a derived rule, right? In general, so I'll say derive, and we'll take a type A, and I'll take dependent type B, and then I'll take a function of pi AB, okay? And what I want to get is, well, I want to get the judgment, the equality judgment of the eta rule, but I don't have it yet, so I'll just say, okay, equality check will prove, so sort of derive, ec.prove this equality. So I want to say the eta rule, which is x, f, is equal to, well, lambda, and I have to fully annotate A, B, and then I say, if we abstract A, app, A, B, F, and A, okay? I want F to be equal to lambda and then app on F. And I had to abstract here because this is how I gave the rule for lambda, you see here. It's an abstraction. Okay. And then what I get at the end will be something in pi AB. And now because, well, I want the equality checker to prove this equation. And I've told you that we think of unfinished goals as boundaries, right? So I say by and 2 question marks, and this is like the current notation for a hole in the boundary, okay? And maybe I did everything okay, maybe I didn't. Parsing error, of course, it happens when you do a live demo, okay? Unexpected in character 50, it will be somewhere here. Oh, right, I concluded it too fast. Okay, let's try again. Okay, and it works. So it actually gives us a rule, a derived rule, a derivation that we can say, okay, if I have a type A and B and F, then I get this equality. So you see, equality checker really said, okay, if we have an extensionality rule and the computation rule, we get the eta rule. Okay, so this is a point where I'll conclude my demo and invite you all for questions.
Okay, thank you very much. So first, let's thank Anja for her talk. It's very interesting. So I'm sure there's lots of questions. If you want to ask a question, please unmute your mic and go ahead.
It's a nice piece of work. I'm going to have to play with it sometime, see what it does for me.
Yeah, well, I'm glad you liked it. It's still a work in progress, so if you will play with it a lot, you might find some bugs, and we'll be happy if you report them. Yes. But I hope it more or less works. But I'm just giving you a fair warning. It's still a sort of experimental phase.
Reporting bugs. I want to find out what kind of thing it is rather than use it for an industrial application.
Great, yeah. So I think it should be, fairly ready by the end of the summer with all the documentation, maybe, or at least part of the documentation, because currently it's kind of hard to figure out. But we have like example folder, we have a test folder, we have a theories folder, and then you can see what happens, sort of. But I think even if you look at this code, you can figure out quite easy what.
I already found some of that stuff on my computer while you were talking.
Well, perfect.
Thank you.
So Anja, can you say something about what happened at the end where it figured out a proof of something? Is this a general sort of proof search, or is it very specific to eta rules? What was going on there?
So I'm not sure what you mean by this question. So your question is, when I say ec.prove here, I just give it a boundary and the equality checker will run through it like I described earlier, and then it will either succeed or will say, well, I don't know what it is.
I see, okay, I see.
So it's just a general boundary. So eta rule is nothing specific here. It's just something that we know can be derived. So I chose an example just to, to give you a little assurance that eta rules are actually derivable from extensionality rules and computation rules.
Right, yes. Okay, yeah, I just got misled by the prove word, but it's just checking a definitional equality from the given rules, yeah.
Yeah, so basically everything, so the judgments that we can obtain in Andromeda are derivable, right? So it sort of says, okay, I have this boundary, but I want to know if I can derive it. And behind the scenes, it really constructs the assumption set that belongs to this equation, right? So behind the scenes, when we say, okay, this is a judgment of this boundary, which is an equality boundary, right? It is just the assumption set.
Okay, thank you.
Thank you for a question. Yes, that clarifies a bit.
Other questions?
Andre just said that the nucleus can handle inversion principles. Have you got a demonstration of how that works?
Yes, so it's basically just pattern matching, right? So I can do something like, I can say something, okay, I need something. So I'll say rule a type, and I will say rule, sorry, I'll give myself some rules so I can show you. Okay, so it's X in a, sorry, what am I doing? A type, okay. Something in a type. And then I can give myself some judgment. So let judgment be okay, and I need something else. I need some constant in a as well. And then I say, okay, let judgment be b applied to a. Okay. So let's see if I what did I do wrong now? Ah, here I have type. Ah, silly me. This is the term judgment. Okay. And when I say inversion principle, that's basically pattern matching. So I say match judgment with, and then I give it a pattern and I say, okay, this will be something of the form B of, and then something X, and give me back this X. And I need an end here. What did unexpected X? What is going on? If either Andre or Philip see what's the syntactic error.
When you're using X after you've matched it.
Ah, here, yes, thank you. Okay, so when I'm matching X, I need a question mark, and when I'm giving it back, I need it without the question marks. Thank you. Okay, so now I got at the end a judgment that A is in A, right? So I matched it, so this is an inversion principle, right? I can match it B, and then I can see what I have here inside, right? Does that answer your question?
Yep, that's fine, thanks.
So interestingly enough, we can match the abstractions as well here, right? So if I had an abstracted judgment, I could write the abstraction here and we could extract the arguments just the same.
More questions? Can you give an example of something that doesn't work well, like some rules that are badly behaved, or something that causes some trouble with the current implementation?
That causes trouble with the equality checker, or just the Andromeda in general?
No, the equality checking algorithm. Are there some rules that someone might actually care about that won't be handled, or does this framework handle the most commonly used rules?
Well, there are certainly rules that cannot be installed as computation or extensionality rules. Especially it's bad if they have some sort of meta variables in them. I know that Philip had a counterexample a little while ago, but I cannot currently remember from the top of my head what that was. But definitely the pattern matching for the computation rules could be better. I can look it up, but I don't think it will.
No,
I think
serve the purpose.
It's fair to say that it depends a bit on your expectations. If you're coming from traditionally computationally well-behaved type theories, then typically people will work very hard to make sure that their rules are sufficiently nice that they would fit into this algorithm. If you're, for example, if you want some commutativity law, then that is not something that is that you should use to rewrite along. But there's,
oh right, yeah, the termination problem. Of course, if you give the rules that you know will not terminate, then you know it's fairly easy to get into trouble.
That's something like a commutative conversion for some sort of type theory that is a fairly common sort of thing.
Yes, yes. Also, the computation rules in the premises don't have any equalities, right? So if you want to use something that has equalities in the premises, then you automatically get rejected, right? So this is, I think,
also the patterns are not fancy enough to be able to figure out how to apply a rule if the meta variables appear inside lambda abstractions, right? So inside, you never pull out a meta variable from an abstraction. So that's the sort of fancier pattern matching, which I think deducti can do, but we don't. I think you could come up with some rules where you would want to do that.
Okay, thank you. Any last questions?
Can we ask Andromeda to show us the derivation eta and see that it used extensionality and an eta rule or something like that? A beta rule, I mean?
Sorry, I didn't hear quite well. Can you repeat it?
Yeah, sure. Can we ask Andromeda to show the derivation that it found and see that it used extensionality and a beta rule, something like this?
No, because it's proof irrelevant, right? So what you see here, what you get here is just the assumption set. So it hides the derivation. I mean, it's derivable,
but it's gone.
And but at this point it's gone. Yes, exactly.
Okay, last call. Okay, well, let's all thank Anja again. All right, so that's it for today, and we resume again for the last day of the conference tomorrow morning at 10:30 Eastern. See you then.